Okay, so question 6 is going to be about turning moments. I can see this here, so I'll get this ready in case I need it. Fat, moody dinosaurs. It says an upward force is used to cause rotation about a pivot. Which row of the table is correct for this? Well, that's the force upwards, and this must be the pivot because the turning moment's going that way. So we've got the arms provide an upwards force and the feet are acting as the pivot. Okay, now we've got biceps, and it says the muscle provides a force to balance the weight of the forearm. So the weight's pulling down and this muscle provides a force. And if the hand was stationary here, that would be in an equilibrium with the total of the anti-clockwise is equal to the total turning moment of the clockwise. So it says use the principle of moments. So we're going to have to state total clockwise and total anti-clockwise. I always state anti-clockwise first because it just enables me, usually with these, you've got that going on, so it's easier for me to just write it. So first part, the total anti-clockwise moment must be equal to the total clockwise moment. And then we just got to do a little bit of maths. So I've got my fat, moody dinosaurs. I'm going to work out the moment. And we've got the weight of the forearm, and its center of mass is there. So we've got 23 times 16 for that force. This one must equal the other. So that's going to be 4 times 92. And if they equal each other, we've proven it. And there we go. So 92 times 4 is 368. 23 times 16 is 368. QED. Point proven. The person then holds a ball weighing 15 newtons in their hand. So we did all the other parts now, and now we've got this additional force. It says calculate the force from the muscle that's needed to keep it in equilibrium. Okay, so we know that it was equal before. We've now got this extra part now where we've got the weight of a ball and a new distance of 32. So we can see, well, we knew before it was 368, plus we've now got this 15 times 32. So now that we've worked all of that out for this side, hopefully that makes sense. We knew it was that from the previous question, and now I've just done the 15 times the 32. So the force times distance again, fat, moody dinosaurs. Now that I've found this side's got to be equal to it. So we can see force equals that turning moment. So it's now move that down and divide by the distance. And we can see that we've got the force from the muscle is 4 centimeters away. So they're just trying to catch you out with adding that in there, which we've used before, I think. Yeah, you see we used it before. Okay, so to go through now, 848 divided by 4 is 212. So this is a question of put lots of information in there. It's you making sure that you've seen that's where the force of the muscle is in that distance. Here's the weight, and it's the total distance from there. I don't need that. Okay, figure 15 shows a ball floating in seawater. Well, what do we know? Well, we know that in each of these examples, weight will equal upthrust. So we know upthrust, the force must be the same because it's the same ball with the same weight. So it says compare the upthrust on the ball in seawater. Now they're trying to catch you out by showing that this one's lower in fresh water. That's just to do with the density of seawater. So the upthrust must be the same because they're both not moving, they're both floating. So upthrust in each case they're equal. Explain why there is less of the ball below the surface of the seawater than the fresh water. So, well, the weight of the ball equals the weight of the water displaced. If this is denser, because we know P equals H rho G, and we've played with this density in terms of pressure and things like that. So the seawater is more dense, it tells us that in the question. So a smaller volume is needed to displace it. And that makes loads of sense. Okay. So this is more dense, so it needs less volume. But the upthrust is the same, and that's what they're trying to catch you out with there. Nice question, not particularly easy.